Okay, so good evening, everyone. So this is the fundamentals of compressible flow course conducted by NPTEL in this Jan to April 2024 session. The instructor for the course is Professor Niranjan Sahu from IIT Guwahati Department of Mechanical Engineering, and my name is Aditya Sharma, and I'm your TA for these live tutorial sessions that we are having in this particular course. So we shall start this particular session in next 5 minutes. Thank you. Good evening. So I believe because it's already 3:05 p.m. So we should start today's session. Okay. I hope I am audible.
Yes, audible.
Thank you. Okay. So this week five is again normal shocks. Uh, in the last week, we the topic of this that week was normal shock, and in that we initiated with the analysis of normal shocks. And in this week's content, so we have moved further. So we are trying to analyze normal shocks from different perspectives, be it the different properties that are linked to the normal shocks, or some limiting cases linked to the normal shocks, or maybe there are some other topics also that have been discussed in this week's content. Okay, so we shall, as we have been doing in these sessions earlier. So first of all, just briefly we'll go through the topics that have been covered in week 5, and then we shall move on to the questions. All right. So let's see the topics that have been first covered in this week's content. Okay. Okay. So the first topic in this week's content was normal shock analysis. So in this topic, first a brief revision of the previous week's content was done by the professor. Then there were some inferences that were deduced based on the previous knowledge of the normal shocks that was discussed in week four's content. So based on that, this subheading related to this normal shock analysis was this limiting Mach number. So you may increase the Mach number to any high value you want, but then there is some limiting Mach number related to that. By that I mean, so if this is the Mach upstream of the shock, if this is a normal shock, right? So if this is our normal shock, so if M1 is the upstream Mach number and M2 is the downstream Mach number, so there is this limiting value of M2. So M2 in any case won't go below this value. And for this, we have this formula, all right? Okay, which is something like this. M2, okay. M2 equals to limit M1 tends to infinity, right? M1 tends to infinity, gamma minus 1 by 2 gamma. So this is how we can calculate the limiting value of this Mach number across a shock. And for a value of this for gamma equals to 1.4, this value comes out to be, right, M2 limiting value comes out to be 0.378. Okay, so this is for gamma 1.4. Sorry. Okay, so Then the next subheading was limiting static pressure ratio, right? Static property ratio. So different static properties and the limiting cases of those properties were discussed in this particular topic, right? So which are as follows. So this is limiting static property ratio, right? So this is for density. For density, it is this, all right. And for gamma equals to 1.4, this comes out to be which is equals to 6 for gamma equals to 1.4, right? And then there is this static pressure ratios. So they go infinite. So if we move across a normal shock and we are dealing with the uh, limiting value of this static pressures across the shock, right? So right, so if flow is in this direction, if flow is in this direction, right? So across the normal shock, uh, this condition will be there, right? And then there is limit m1 tends to infinity t2 by t1. So same is the case for this static temperature also. So if there is a normal shock with this downstream upstream Mach number tends to infinity, in that case the static temperature downstream of the shock will the ratios of these two static temperatures will be infinite. Okay, so this is our limiting static property ratio, right? So next is the uh, entropy conditions, right? So in this, basically it was discussed a formula of this S2 minus S1 was given in this particular entropy conditions. So in this entropy conditions, so I'm not going to write this formula, right? So such formula has already been discussed in the last week's content, right? But then some inferences have been taken from this analysis of normal shock waves based on this formula, right? So one important inference that I felt is very important is that for subsonic shocks, right? For subsonic flows, sorry, not shocks, for subsonic flows. So the change in entropy is negative, right? For subsonic flows, the change in entropy is negative, right? So this condition is not possible thermodynamically, all right? So in that case, which means, so this has been analysis has been done taking into consideration. So taking into consideration. So if we suppose in subsonic flows there is a normal shock. So if we use these entropy change formula, what happens? What value do we get? So in that case, we get a negative S2 minus S1 value change in entropy, which is nothing but S2 minus S1. Okay. So in that scenario, we see that this value is negative, and which essentially means that this flow is not possible, right? This situation, this physical situation, physically it won't be possible. So from this mathematical expression and value of m less than 1, it can be deduced that for subsonic shocks, the normal for subsonic flows, normal shocks won't be encountered, right? So this fourth inference, which is stagnation property ratio. Okay, so yes, so similarly, the stagnation property ratios have been discussed. So we have encountered the stagnation properties in the previous week's lectures. So one such case is this stagnation temperature. So we know that from the previous week's content that across a normal shock, as energy must remain conserved, so the stagnation temperature T1 remains equal to T2, right? Stagnation temperature, this remains constant across a normal shock. So this was about the normal shock analysis, right? Then one very interesting topic we came across, right? So this is Krokow's theorem. Okay, so if you see Krokow's theorem, so what does a Krokow's theorem do? So it relates the fluid vorticity, right? Vorticity and entropy change. So Krokow's theorem states that if there are entropy and enthalpy changes in a flow, in that case, we can relate that to the kinematic properties of the flow, which the theorem mainly is trying to convey that by just having the this thermodynamic changes in the flow, we can predict the kinematic behavior of a flow. By kinematic, here we are concerned with only the rotationality or irrotationality of a flow. So in fluid dynamics, uh, we are introduced to whether flow is rotational, irrotational, steady, unsteady. In the initial this fundamental course of this fluid dynamics, we are introduced to this thing. So uh, vorticity like is 2 into this angular velocity, right? And then angular velocity is this. Just I'm writing this the mathematical expression for this. So um, because we don't have any question based on these formulae in our assignment, so we won't like be practicing questions based on this, but we must know like uh, what these things are, and we must be able to mm, uh, solve any problem based on these formulae, all right? So these concepts we should know. So like curl of velocity, how to find a curl of velocity, which is basically nothing but this vector operation, right? So there is a cross product and there is this dot product. So this is basically a cross product. So that we should know how to find a cross product, and so that we can move uh, ahead if there is some uh, problem related to this concept, right? So then there is this relation linked to this. I'll just write this so that we have this idea of what this equation looks like. All right. So this is the uh, expression from Crocos theorem, right? So this is the enthalpy term and this is the entropy term, right? So we have related this with the velocity term, right? Enthalpy term, this velocity term, which is velocity term means the kinematics is involved in this particular theorem, right? This is enthalpy term and this is entropy term. All right. Okay. Then the gas property tables for normal shock relations were discussed. So gas property tables for normal shock relations. In week 4, we came across various relations related to normal shock waves. So these were briefly like pointed out in a particular slide in lecture 12, I believe, the at the end of lecture 12, and then a uh, table based on those relations was presented, right, by the professor. So this was about the gas property tables, and we have numerical also in this particular assignment 5. We have numericals, 4 numericals based on these relations, compressible flow relations, normal shock wave relations. So we shall see in this particular session, try to solve 3 4 numericals, 4 I believe numericals we shall try to solve based on these property relations only. All right. So this was about lecture 12. Right. Okay. All right. So then there was this thermodynamic analysis of compressible. So in the lecture 13, the professor initiated with this thermodynamic analysis, right? So in this lecture, we have now started seeing a normal shock as a compression tool. Okay, so we not want, but by virtue of the this quality of normal shocks, that there is a natural compression in these shock waves, because across a shock wave there is increase in the static pressure, right? So we are looking towards normal shock from that perspective now. Okay, so thermodynamic analysis of compression process. Okay, right. So a graph has been given there, right? So this was, I believe, pressure and the specific volume graph was there, and it was something like this. Right. So this was, and this was. So it was something like this, right? So this was polytropic tropic process was being represented with this particular this expression, right? So in that case, the value of n decides about the behavior of this particular gas or flow or the gas in the flow. So that has been discussed in this uh, particular topic, right? So if for example, if n is zero, if n is zero, then this whole term becomes one, right? So in that case, there is no use of including v in this particular expression, right? So it becomes independent of v. So in that case, the this expression corresponds to a process that is isobaric in nature, right? Isobaric in nature. So in this fashion, different processes have been discussed in this particular slide, right? Okay. Then if you see, so like I was just telling that we have started seeing shock wave as a compression medium. So this has been discussed in this particular in this particular heading of lecture 13. And then the professor moved on to this Huguenot relation, right? So Huguenot relation is basically nothing but we are trying to find some properties related to this flow across the shock, upstream of the shock, downstream of the shock, and such ratios of the properties of a flow in such a scenario we are trying to find using this Huguenot relations. And one different thing or uh, uh, important thing about this Huguenot relation is that here we are not taking help of either Mach number or velocity, right? So we are not using, not taking help of velocity or Mach number to get to the ratios of the properties upstream and downstream of a normal shock. So this is the Huguenot relation. Then there is this few expressions from Huguenot relation, right? Expressions from Huguenot relation are something like this, right? Right. So this is one particular expression from this Huguenot relation, and then there is another, right? So there is one more relation, right? So P2 by P1 equals to right. So I believe minus 1. Okay. Please correct me if you see some mistakes on here. All right. So then there was this one graph also related to this Huguenot discussion, right? Done by professor. So I'll just briefly draw this. Then we move on to our questions. All right. So something like this has been drawn, right? So these two states have been mentioned. All right. So also there is one line which joins point 1 and 2. So if there are two states in this flow, right? One is upstream and one is downstream of this normal shock. So if we join these two points, sorry, so what we get is a Rayleigh line. So basic terminology, we should be aware of this, right? Okay, all right. So now I believe we should move on to our questions, because this brief discussion of this, the topics that have been covered has been done. So then there was this last topic was isentropic compression versus shockwave compression. So in this, nothing special has been done. What has been done is, so graphically it has been shown that how the two processes are differing from each other, right? So if these are the two processes, so the continuous one is this isentropic, okay, compression, and this one is this Rayleigh curve, right? This one is a Rayleigh curve. So this 1 point and 2 point. So across a normal shock only the discussion is we are having across a normal shock. So in this case, if there is compression, so in real case, how the compression will be, and in the ideal case, the isentropic case, how the compression will be, this has been discussed. All right. So let's move on to the questions. Okay. So the first question is all the flow properties undergo finite but very large change across the shock wave in dash manner. So yes, there are four options. So in a shock wave, the properties change are in which fashion? Whether it is isentropic or non-isentropic or non-adiabatic, or we cannot commit.
Non-isentropic.
Okay, right, correct. So you know this, right? So the properties change across a normal shock will be non-isentropic, right? So as we have discussed in the previous classes also, that the isentropic thing we deal with just for the sake of mathematics, and to make things easier for us in terms of mathematics, so that we have a reference for our real world problems, right? Okay, so this was the first question. So let's move on to the next question. Limiting Mach number is a function of. Okay, yes. Limiting Mach number is a function of.
Specific
Either
heat, CC.
C. Okay. Okay, you say C. Right. So what is the expression for limiting Mach number? I have just mentioned it. So I'll just, for the sake of recording also, I'll just mention it again, so that you can directly refer to this only. So this is the expression, right? So specific heat, this is specific heat ratio, right? This is nothing but specific heat ratio, right? So the correct answer obviously is C, right? Okay, so let's move on to the next question. Okay. So the thing is, you keep the Mac number whatever high value you want to keep, but then there is one limit below which it won't be possible to, it won't be in the capacity of the strength of the shock to lower the Mach number downstream of this shock. Okay, so for 1.4 gamma value, this is 0.378, right? So this I have already mentioned. Okay. Okay, this also I have just mentioned. So this is right. So this. So there are polytropic processes like this, and this is n equals to 0. Let's suppose this is n equals to 1, this is 2, and this is 3, right? And this is n infinity, right? So PV n equals to constant, right? This is a polytropic expression. So for this case, it will be
A.
A, right? Okay, isobaric, right? So only mm, in this process, only pressure, no, only yes. So pressure will remain whatever the volume of this process be. So pressure will remain constant. Okay. So this is our answer, right? You see this. This is our answer. Sir A. Okay, right. Thank you. So, go on to next question. Yes. Right. No answer?
D. D.
B, you say B. B for ball. You said B, right?
D. D.
You said D.
Uh,
Okay,
C.
okay,
D.
okay, right. So this is nothing but Rocco's theorem, right? This Rocco's theorem only, and this is this definition of this Rocco's theorem. So if it says that if there is this change in the thermodynamic, these two properties, in that case the flow will be rotational, right? So that you just mentioned option D. So this is the correct option, right? So when the flow has a gradient of enthalpy and entropy, the flow will be rotational, right? We just saw this expression, right? This is the Krakow's theorem. Okay, right. So D option is correct. Then let's move on to next question. Okay. The initial point on the Hugonoid curve corresponds to Mach wave. Let me draw first a Hugonoid curve, right? All right. So this is our Hugonoid curve, right? So with reference to this Hugonoid curve, the initial point, right? The initial point will correspond to a Mach wave. Is this statement right or not?
True. A.
Right. So this graph I am showing for some random normal shock, right? But then we know that Mach wave, we get a Mach wave when the flow just has become supersonic, right? When the Mach value has just reached this value of 1, right? So in that case, if you see across this Mach wave, what are the properties changed? So these changes are very feeble, right? Very weak. And in this Hugonoid curve, this initial point corresponds to this Mach wave only, right? So yes, this is also true. Okay. So these questions are basically to revise whatever content is there in the in the lectures, right? In the slides of the lectures. Apart from this, one must go through the references, right? As per the interest and as per whatever one expects from a particular subject. So one should like move in that direction only. So this is a these are very basic things, this from the perspective of the content that has been provided, or that has been discussed in the lectures of this particular course. But then this is not only the content that one must constrain oneself to, right? Limit oneself to. So references must be like gone through, right, as per one's interest. So that is very important. So yes, this is true that the initial point on the Huguenot curve corresponds to Mach wave, right? Okay. Then we have this also I have discussed, right? For a subsonic flow, the entropy decreases across a normal shock, and for subsonic flow, and which is a possible situation, right? Yes.
False. B.
False. B. Okay. Right. So I have just discussed also, right? So in a subsonic flow, the entropy decreases from this. Uh, I have not written it, right? I have not written it, but I should. Let's just write this expression. Write this expression. Yes. So this is question number 6, right? So the expression for this entropy changes Cp ln. So this is some function of, right? Or maybe just I should write some function of m1. This is function of gamma r and m1, right? So this is this, but then if your m is less than 1, so in that case this s2 minus s1 will be negative, and which is thermodynamically not possible. So this statement is false, and it is not possible to do so. Right? Okay. Now, so we have this numericals from question number 7 to 10. So first of all, I want you to please note down these values, and based on that only we shall proceed further, right? So I'll also note down these values, right? Values for question number 7 to 10. All right. So upstream of normal shock, right? Shock values are given. V1 is given as 1500 meter per second. Right. Let me just check. Yes. This. Then static pressure upstream of normal shock is given as 13,000 Pascal, right? Static pressure is given as 205 Kelvin. Gamma is given as 1.4, and then R is given as 287 joule per kg Kelvin. So these are the values given. Let me know once you have noted down these values.
Yes, not.
Okay, noted. All right then. So this is the first question. Find the stagnation pressure downstream of the shock. So how do we find stagnation pressure? This is question number 7. Stagnation pressure has been asked. Right. And right, okay. So downstream of the shock, this has been asked, which is P02. Right. You write this or this. Okay. So this has been asked. All right. So how do we solve this? Any idea?
We can use Rayleigh multiplication
Okay.
or else P0 2 by P1 relation. Yes.
All right. Okay, let's see then. If we want to use P0 by P, then let's see how to proceed. Right. So
We need to
for
find M1 Mach number.
yeah, right. You're right. So a Rayleigh relation, if we need to use, right? Rayleigh relation is 2 by P1 is 2 gamma plus 1 divided by 2 M1 square gamma plus 1 divided by 2 M1 square divided by 2 gamma M1 square divided by gamma plus 1 gamma minus 1 by gamma plus 1. This, right? Okay. Then you said we need to find M, right? So how do we find M? M1 is V1 by A1, right?
Yes. We want to find A, square root of gamma RT. V1 is given.
Right. So gamma is also given. What is T? T is 205, right? T1 is 205. Right. So if we solve this, this comes out to be
287.
287. Yes. 287. Wait a second. Okay. So M1 is 1500. How much?
5.226.
226. Okay, 5.226, right? All right. Then we now use this Rayleigh relation, right? So let me write it this way: P naught 2 by P1. So yes, we know P1 है ना? We know P1 and P naught 2 we can find out. So gamma is, I'll just put the values in the, this is 5.226 square, right? So this is then 1.4 plus 1 divided by 2 and 1 square, which is 5.226 square, divided by 2, 1.4, and then 5.226 square divided by 1.4 plus 1, then minus 1.4 minus 1 divided by 1.4 plus 1. Okay, then this whole raised to power 1 divided by 1.4 minus 1, right? If I'm not wrong. So let's calculate this. Yes, what value you are getting? Still calculating. Yes. Oops. That's for my calculator. Yes. How much this comes out to be?
0.44786 megapascal. P02.
Wait. So you're telling me the P not 2 value, right?
Yes, yes.
Okay, wait. 8. So this will be around, this ratio will be around 35.6836 from my this, right? And then P not 2 will be 6836 into 15. Oh, sorry. Yes. So I'm getting this. I'm getting something like this: 463,888.095 Pascal, which is 0.46 megapascal, right? So let's see this answer is. So you said 0.44 megapascal, right?
0.44786.
Yes, 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 yes. So it will be in this range only, okay? So this is how we can
Yes,
solve.
I have one
Yeah,
doubt on this. Actually,
yes.
a Rayleigh formula we can use relation. Other than that, can we use this gas in gas table? We have right one formula, gas relation, normal shock. Last lecture we had one
Which
gas property tables for normal shock relation. In there we have P naught 2 by P1, 1 plus gamma minus 1 by 2 M1
wait,
square
wait, wait, wait. You're talking about this lecture
to find
12 or
static.
lecture
Yes,
12 or lecture?
lecture 12. Next to Crocos theorem, we had one formula, right?
Okay, okay, wait, wait,
Gas
wait, wait,
property
wait, wait.
table. Yes.
Yes, yes. Now say in
That
gas property table.
normal shock relations we have, right?
Yeah, in summary, right?
Yes. In the P naught 2 by P1 one formula we have, right?
Yes, P naught 2 by P1.
Yes, 1 plus gamma minus 1 by 2.
Right.
This relation can we use to
No,
calculate
this
stat?
is because we had to find P naught 2 by P naught P1, right?
Yes. Can we use this relation to find out the P naught 2 value? Because we know the P1, M1 we will be finding. After that, we have the value of gamma. So,
Acha, from here
yes,
you want to find P naught 1, right?
P naught 2, P naught, that last,
But then how would you find M2,
okay, P naught
right?
2. Oh, no, that second is P naught 1 or 2. Oh, sorry, it is P naught 1. Okay, okay. I thought it is
Yes.
P naught 2 by P naught 1,
Yes, yes,
P1.
because
Oh,
there are lots of this relations revolving around these 1 and 2, so there are chances of getting confused. So that is fine.
yes, I know, I understand. I from my point where it looks like for me P naught 2 because I was solving with this. I'm not having this two relay relation and this two. I didn't get the same value for P naught 2.
Okay, okay,
The values were different. That's why I had a doubt. Okay, okay, it's
all
P naught
right,
1.
right. So it's 4-4, right? Let's take
Mm,
one break, 5 minutes break, five
okay,
or 10 minutes break, then we'll start,
okay,
right? Okay.
okay.
Okay, then let's move ahead with the session, right? If you're there. Yes, Ginny, are you there?
Yes, yes.
Okay. Okay then. So you're done with this. Okay. So let's move on to next question. Find the stagnation temperature downward of the shock. Yes. So this is pretty straightforward, right? Because such questions have been asked in your assignment. That's why I am giving these questions in this particular assignment. Otherwise, we have, I believe, discussed such questions in previous assignment, right? So if you see, so stagnation temperature has been asked in the downstream shock condition, right? So but we have this upstream static temperature value, right? So we have T1 equals to 205. But we also know, right, that for normal shocks, right? Why I'm saying this? Because we know this expression, or T naught, this we know, right? So what we can do is either we know the value of M2 or we know the value of M1. But here from the previous question only, we know that M1 is 5.226, right? So what we'll do, we'll write it like this, or maybe initially let's write it like this. T naught 1 by T1. This is 1 plus gamma minus 1 by 2 M1 square. Right. But then because T1 equals to T2, we can write it like this. That is implies 5.226 का square, right?
Answer is 132.24 points something.
Okay.
1320.
132 What?
1324.754.
Oh, 0.75, right? Right. Wait. So under 5.4, 4.622. So this is, oh, I not written T1 here. Sorry, T1. 622 into T1. 6.4622 into 205, which comes out to be this 4.75, right? Right. So if we see the answer to this question, so it falls in the range, right? It falls in the range given. Okay. So this was about stagnation temperature. Previously we did stagnation pressure using Rayleigh relation, right? Here we used isentropic relation, right? So moving on to next question. So find the static pressure downstream of the shock, normal shock. So how do we find this? Using which relation?
P2 by P1 equals to 1 plus 2 by gamma plus 1. M1 square minus 1.
Okay. Let's do it then. P2 by P1 equals to 1 plus 2 gamma by gamma plus 1 m1 square minus 1. Okay, okay, okay. Okay. 2.8 divided by 2.4 into 26.311 0, which is plus 30.6161, which is 31.6961, implies P2 by P1 is this, implies P2 is P1 into 0.61. P1 is 13,000, right? Oh, sorry. Into 31.6961, which comes out to be 1 Pascal, which is 841 megapascal. Yes, are you getting the same value?
Is 0.412.
Okay. 0.412, right. So this was question number 9, right? So this is our range and our answer fell in this range. All right. Let's see the next question then. So find the static temperature downstream of the shock. Let's solve this. Yes. So how do we do this? Right. So we have this value of this expression, right? 1 plus 2 gamma by gamma plus 1. 2 plus gamma minus 1. Gamma plus 1 square plus T2 by T1 equals to 1 plus 2 1.4 1.4 plus 1, right? M1 square is 5.226 square minus 1, right? And then is 2 plus 1.4 minus 1, 5.226 square, 1.4 plus 1, 5.226 square. Please let me know if there's some mistake in this particular expression. Right. 1 plus 2.8 divided by 2.4, 5.226 square minus 1 equals to 26.3110. This is 2 plus 0.4, 0.4, and this is 27.311 divided by 2.4 and 27.3110. This becomes this is 31.6961, right? And this is 0.1971. So into okay. So this is T2 by T1. Okay, this comes out to be 1 to
One.
A to, yes, you're getting the same value.
Yes, yes.
Okay. Okay. Right. So now we are done with 10 questions, right, of the session. So, all right. So let's move on to some extra questions, right? It's because there are 10 questions are asked in your this assignment. So I just prepared first 10 questions and then I thought I should keep the additional questions in the next section of these slides, right? So we have this question from lecture 12, right? From lecture 12. The first lecture of this week, and from there, sorry, the first topic, right? So normal shock analysis, and from there also this limiting static pressure ratio topic. This question is, so the question is the static pressure and density ratios across a shock for gamma equals to 1.4 R. So let's first of all see, because we are left with half an hour, so we can just okay. So what has been asked? Static pressure has been asked, and static density has been asked. So I believe I have like discussed these in the topics covered, right? So this is nothing but limiting pressure, right? This is infinity, and this is limiting what? Density. This is, so in any case, the ratio won't be beyond this value, right? So for this is nothing but 1.4 plus 1 divided by 1.4 minus 1, which is 2.4 divided by 0.4, which is 6, right? So which option will be correct? So first pressure has been asked, then density has been asked. So pressure is infinity. So there is only one option, right? In which, because I have used this respectively word also. So
Yes.
it will, yeah, A is the answer, right? Okay. Now let's move on to next question. Right. So this is from again from lecture 12, right? Stagnation property ratio. So the question is, what happens to the stagnation density across a stationary normal shock? Oh, this is very straightforward. Yes.
Constant.
Remains constant.
Sorry, decreases. It will show decrease.
Decreases. All right. So this there are these values of pressure and density. I believe these decrease across the normal shock, right? So there is only energy that remains conserved. Also in the pressure also there are losses. Okay. So as I had discussed that for the intakes, supersonic uh, these aircrafts, the intakes of their engines need to minimize the pressure losses while they are taking these while they are taking in the air. So across the normal shock, there is always this pressure loss. From this table also, right? From this gas property table also, you can just figure this out. So if you see across some particular normal shock of some particular strength, if you see there, you will see that the P1 P naught 1 is not equal to P naught 2, so there are differences, right? So if we see the answer to this question, so it decreases, right? So rho naught 2 is less than rho naught 1. P naught 2 is less than P naught 1. But T naught 2 is equal to T naught. This we must remember if we are studying normal shocks, compressible flows. So we should remember this. All right. So this was question number 12, right? Then let's move on to next question. So compression through a shock wave. All right. It's a totally non-brainer, right? So, because I have said this, that I've already mentioned the topic of this question, right? So shockwave is a thermodynamic device of compression. So this particular sentence is from, but we should remember this, all right? So the main thing is that we should remember that the shock wave is a thermodynamic device of compression. All right, nothing would come here. It's a of compression. All right. Okay. Yes. What is the answer to this question?
D.
D. Are you sure? Right. So Huguenot relation is, let me just again write this. So Huguenot relation, let me write this. All right. So yes, this is applicable for all the gases, right? Right. Okay. So two equations we can use, right? So let's move on to next question, right? Right. So this. So I have discussed this, right? So this is this. This is this. So this is Huguenot curve, right? This is state 1, this is state 2. And then if you join this, this is really line. Yes. Yes, what is the answer to this question?
D.
D, right? So you know this, right? It's from your slides only. The direction of this Rayleigh line matters, right? So it cannot be in the downward direction. So this specific volume has to decrease, right? So this is in terms of thermodynamics, that if it happens that the direction of the the change in the state of a particular gas in the flow is in such a fashion that it moves from 2 to 1, then it violates the second law of thermodynamics, right? So this is it. And then right, so this is D option is correct, right? So let's move on to next question then. So this is, I believe, the last question of this session, but then after that we shall do one more numerical, because we are left with 15 minutes, right? So we shall solve one extra numerical, and then after that we shall call it off for today. All right. So this is it. Question number 16. So the topic is isentropic compression versus shock wave compression. So as I've mentioned, right? So this is it. This is pressure and here is specific volume. Something like this. So if let's see, they join here and they join, let's say, join here, right? This is 1 and this is 2. So for a given decrease in volume, right? So let's say this is V1 and this is V2, right? So decrease in specific volume. So across a shock wave, we know there is decrease in specific volume, right? So in that case, this shock wave will create a dash pressure increase. So the pressure increase with respect to this isentropic case for this Hugenoid curve, right? So we know this is Hugenoid curve. Hugenoid curve, and this one is isentropic curve, right? So two curves are here, right? So if there is this decrease in this specific volume from V1 to V2, so in that case the pressure change, right? So these, if you can see, so if we see these uh, vertical lines, right, for a particular specific volume case. So if we see for V1, this cuts here, right? And if we see for V2, this vertical line cuts Hugenoid curve at this point, right? And for isentropic case, it cuts at this place, right? So for these two states, there are two different types of pressure changes, right? So I just rub this out. So either there is this pressure change, right? So this pressure changes for for Huguenot case, right? Then for this isentropic case, this V2 line is cutting at this particular point, right? And this particular point in the y-axis corresponds to this point, right? This is the second state after the shock, right? And this point is before the shock. Before the shock points are common for both the cases, right? So like we have initiated from a common case, and then we are trying to see what are the pressure jumps for the two different cases, right? So if we see this another case, right? So for this value is smaller than that. Let me just so there are two cases. One is this and one is this. So this is for this and this is for pressure change for isentropic case. So clearly for the isentropic case, this is small in comparison to the Huguenot case, right? So if you see the options, wait. So a shock wave creates a for a Huguenot case, for actual this shock wave, this will create higher or lower. Yes. Now you can comment on this.
Higher. A.
Higher. A. Right. Okay. So I believe this is it as far as the prepared questions are concerned. Right. So today we had discussion on this normal shock wave, right? Normal shock wave analysis. So there we discussed the topics related to this week 5 lectures, and then we moved on to some questions related to that. And yes, we did some numericals and some concept based questions we discussed. All right, so okay, then I believe we should then call this off today, and then we shall meet in the next session, same time, same day, right? Total 12 such tutorials will be there. But I believe I need to prepare some more questions because from last tutorial also I was seeing that we are getting enough time, right? So I'll see from next session onwards. I'll prepare some more questions, right? So that we have like more questions in our hand to discuss. All right. So we shall then call this off here and now. All right. Thank you then.
Thank you
for attending the session. All right.